Okay, for each system given below, and I have two systems we're going to do this for, we're going to find and classify all the equilibrium points, sketch the phase portrait near each equilibrium point, and then try to stitch together a rough portrait of the nonlinear system. Okay, so I have to make a Jacobian. Well, first I need to find all the equilibrium points, and it says hint there are 2. So I set each of my derivatives equal to 0, and I'm going to try to solve. So I get y equals 2x. So in my other equation, whenever I see a y, I'm going to put a 2x. So I get negative 2x plus x squared equals 0. Factor out an x. And then we get x equals 0 or x equals 2. So I have 2 x values that go with my one y value. Oh, sorry, I have 2 x values, and I need to get y values that go with each one. So y is 2 times x, so 2 times 0 is 0. And y equals 2 times the other x, 2 times 2, y equals 4. So my equilibrium points are 0, 0, and 2, 4. So that's my part A. Part B is to sketch a phase portrait near each equilibrium point. So I need to make a Jacobian matrix, which is the partial of f with respect to x and y. So for the x prime equation, the partial with respect to x is -2. The partial with respect to y is 1. And for the y prime equation, the partial with respect to x is 2x. Partial with respect to y is -1. And then I'm going to find the Jacobian at 0, 0. So that would be -2, 1, 0, -1. And I might as well just do the work all out for this one, and then I'll start again for the other one. Okay, so my eigenvalues I find by taking the determinant of a minus lambda I. So I'm going to have -2 minus lambda, 1, 0, and -1 minus lambda. That is -2 minus lambda times -1 minus lambda minus 0 equals 0. So I have 2 eigenvalues. Lambda equals -2 and -1. So this is a sink. It's going to have 2 straight line solutions, and it's a sink. So the straight line solutions I get by solving AV equals lambda V. Lambda, we'll do the -2 first. So I get -2x plus y equals -2x. So if I add 2x to both sides, I get y equals 0, which means an eigenvector would be 1, 0. And then I'm going to do the same calculation for the other eigenvalue. So -2x plus y equals -x. So y equals, I'm going to add 2x to both sides, and I get y equals x. So 1, 1. So I now have all the information I need to sketch a phase portrait around the point 0, 0. When I'm close to the point 0, 0, I've got my straight lines, and I know that it's going to be a sink. So let's see, I'll do a really tiny sketch right here since I'm running out of room. So 1, 0 is the x-axis. So that's one of my straight line solutions. The negative eigenvalues, so they're pointing in. And my other straight line solution is 1, 1. So that's that one. Again, negative eigenvalue pointing in. This one was lambda equals -1. This one is lambda equals -2. And then you sketch the other solutions by starting parallel to the faster eigenvalue, which means the eigenvalue that's further from 0, and coming in tangent to the eigenvalue that's closer to 0. So we're going to start parallel and come in tangent. So something like that. Parallel to the -2 and tangent to the -1. And then it'll look something like that over here. And then same thing in between here. So I want to be parallel to the -2 and tangent to the -1. That looks weird. Okay, I think it just doesn't bend that much. It just kind of goes like that. Like that. So there's my sink at 0, 0. Now I'm going to do this whole process again, instead using 2, 4 as the point that I plug into the Jacobian. So I have to start over with the Jacobian. So -2, 1, 2x, -1. Okay, I've copied the Jacobian down, and now I'm going to evaluate at the second equilibrium point, 2, 4. So I have -2, 1, -1, and I have to replace this x value with a 2, so I get 4. And now I'm going to do find the phase portrait for this linearized matrix A. So I calculate the determinant of A minus lambda I. So that's going to be -2 minus lambda, 1, 4, -1 minus lambda, which is -2 minus lambda times -1 minus lambda minus 4. Set that equal to 0. So I multiply that out and I get 2 plus 2 lambda plus lambda is 3 lambda plus lambda squared minus 4 equals 0. So this is lambda squared plus 3 lambda minus 2 equals 0. I believe this is going to factor to lambda, maybe it doesn't factor. Yeah, I'm pretty sure this doesn't factor, so we're going to do the quadratic formula. So lambda is -3 plus or minus the square root of b squared minus 4 times a times c all over 2a. So this is -3 plus or minus the square root. 9 plus 8 is 17. Okay, so those two irrational eigenvalues turn out to be 0.56 or -3.56. So one positive, one negative. So this is going to be a saddle. I just need to find the eigenvectors to get the straight line solutions for my phase portrait. So to do those, I do AV equals lambda V. And I get -2x plus y equals 0.56x. So y equals 2.56x. So an eigenvector might be 1, 2.56. And then my other one, I'm going to get -2x plus y equals -3.56x. When I add 2x to both sides, I get y equals -1.56x. Yeah, okay, so an eigenvector would be 1, -1.56. And then I can sketch a really tiny phase portrait here. And this one's not at 0, 0, it's at 2, 4. There's my equilibrium point, and we treat that like the origin. So I'm going to put my straight line solutions, 1, 2.56, just kind of a steep straight line solution. And that was associated with a positive eigenvalue, so the arrows point out. And then I have 1, negative 1.56, so something like that, as my other straight line solution. And that was a negative eigenvalue, so those point in. And I draw in my saddle parts. So there's my tiny solution near the point 2, 4. Last thing I'm going to do is try to stitch my two pictures together into one picture. Okay, so I have drawn a larger XY plane, and I've put in the phase portrait at 0, 0. This is the linearized version at 0, 0 and the linearized version at 2, 4. I want to kind of try to stitch them together. So, let's see, I'm thinking that something's going to get captured into, going to get pulled in towards this origin. So maybe this saddle is eventually going to get close enough that it pulls in towards this origin like that. Same with this. And then this might stay away long enough, but then it gets pulled in like that. Something like that. This is really guesswork of how this is going to work. So there's my stitched together guess of how these might interact with each other. Oops. Okay, so for this one, I'm just going to get you started by finding the equilibrium points, and then I'm going to let you finish it on your own. So we need to set x times 10 minus x minus y equal to 0, and y times 30 minus 2x minus y equal to 0. So this is a product, so obviously x equals 0, and over here y equals 0 are parts of the equilibrium points. So 0, 0 is going to be one of them, definitely. All right, and then I have 10 minus x minus y equals 0, and 30 minus 2x minus y equals 0. So I'm going to take this x equals 0 that I got from equation 1 and plug it into equation 2, and I get 30 minus y equals 0, so y equals 30. So that gives me 0, 30 is an equilibrium point. When x is 0 and y is 30, we have an equilibrium point. And then I'm going to take this y equals 0 and plug it in over here, and I get 10 minus x minus y 0 equals 0, so x equals 10. So when x is 10 and y is 0, I have another equilibrium point, and then also 0, 0. When they're both 0, both equations equal 0. So there's the three equilibrium points. The Jacobian matrix, I'm going to distribute my x, so I get 10x minus x squared minus xy, and 30y minus 2xy minus y squared. So my Jacobian matrix is going to be the partial of the x prime function with respect to x. So that would be 10 minus 2x. And then with respect to y, I get negative x. And then the other equation with respect to x, I get negative 2y. And with respect to y, I get 30 minus 2x minus 2y. I think I messed up the first one. This one with respect to x would be 10 minus 2x minus y. Yep. And then with respect to y would be negative x, and then, yeah, okay, good. So that's your Jacobian. You're going to plug in each of your 3 equilibrium points and work out the linear system that results from each one.